Hello, and welcome to this e-learning module organized by the European Coastal Awareness System project. My name is Jesus Palomar. I'm a member of the Geoenvironmental Cartography and Remote Sensing Research Group from the Technical University of Valencia, Spain. In this module, I will introduce you to SAET, a new tool for automatic shoreline extraction using satellite imagery. This module has been divided into the following sections. First, we will talk about what is SAET and what is SAET V, what is SAET's role within the ECFAS project. We will see in detail how SAET has been designed. After that, we will pay attention to several technical details, installation, users' prerequisites, parameters, etc. To continue with an example of use and finally some conclusions. SAET is a new open source tool focused on the automatic extraction of shorelines with sub-pixel accuracy from satellite images for the study of the morphological changes caused by coastal storms. ECFAS is an European project that aims to implement a coastal flood awareness system using Earth observation and non-Earth observation products from ESA, Copernicus, and its contributors. ECFAS workflow is divided into two main parts, the warning system and the mapping products. In this context, SAET constitutes a tool capable to provide accurate shorelines that enable to assess the pitch changes and to elaborate the mapping products, such as the recovery mapping. According to the ECFAS project requirements, SAET has the following characteristics. SAET is an open source tool. It has been developed in Python language and can be run in command line style. In order to prevent commercial dependencies, SAET uses official data sources. In this case, SAET uses three data sources: Sentinel-2 images from ESA, Landsat-2 and 9 from USGS, and an auxiliary polygon layer with the beach areas obtained from the Copernicus Land Monitoring Service. This polygon file will be used to focus the extraction algorithm only in the beaches. Storms affect wide coastal sectors. Therefore, SAET is able to analyze entire satellite images as scenes. In these pictures, we can see how just a few Sentinel-2 tiles or Landsat scenes can cover wide affected areas. ECFAS demands robots and accurate algorithms to the shoreline extraction process. In this context, SAET applies a sub-pixel algorithm based on SHOREX with two main steps. First, the approximate shoreline at pixel level, or APS, is obtained. Basically, this process is performed by computing a water index, which will be used to determine a binary land-water interface, and finally, the approximate pixel shoreline. The APS line is used along with the shortwave infrared 1 band, or SWIR1, as input to perform the sub-pixel extraction. The SWIR1 band is used due to its very good contrast between land with high reflectance values and water with low reflectance values. Second part consists of the application of the core sub-pixel algorithm that is based on a neighborhood analysis of the SWIR1 band, taking as a scanning cell each single APS pixel. The goal is to compute the minimum curvature line in the analyzed surface, which will coincide with the sub-pixel border detected between land and water. To do this, the original values are resampled to increase their resolution. Then, a mathematical function is fed and the Laplacian operator is computed. Those contours, where the Laplacian operator is 0, will be considered as shoreline sub-pixel point candidates. As the scanning cell is moving, there will be a lot of candidate points in the same zone. For this reason, the last step will be to obtain the average position of all the candidate points. These average points will be part of the final extracted shoreline. Finally, one of the biggest advantages of SAET is flexibility. SAET has been designed to adapt to a wide range of the scenarios and user needs. In this context, SAET allows choosing among 4 running modes, 3 types of water indices, several methods of thresholding, and multiple types of vector files for the extracted shorelines. Moreover, SAET allows to modify the beach polygon file by adding, deleting, or modifying the existing polygons. This is especially important since by adding new polygons, SAET can be applied to any location around the world. This picture shows the whole workflow of SAET. It can be divided into 4 main phases. Downloading the suitable scenes from ESA or USGS according to the storm date and area of interest. Segmentation, where the approximate shoreline pixel line will be obtained. Masking, where this approximate shoreline pixel line will be masked, removing those pixels which are outside any beach polygon or removing any pixel covered by clouds. And finally, the subpixel extraction using the aforementioned algorithm. Regarding the installation of SAET, you only have to copy the folder of the tool to your computer. The main files and subfolders in SAET are the following. Aux data folder contains the beach polygon shapefile and the grid shapefiles for Sentinel-2 and Landsat-8 scenes. These files are used to help the user to plan the downloading of the scenes. GDAL Python wheels folder contains a special version of the GDAL library only in case you have problem with the installation of this library. SAET config.py file, this is the configuration file and includes parameters that controls several parts of the tool. We will see this later. SAET tools.py file, this file contains all the main functions of SAET. And finally, SAET run.py file, this is the file that will be run on the command line to start SAET. To make SAET run, first you must install Python and the suitable extra libraries. You must install Python in the version 397 for 64 bits. In this link, you can download Python. The libraries that are needed to run SAET are those that are described in this table. In order to avoid problems, you can try to install individually every library using the pid command. This is an example of how to install the NumPy library. Finally, it is necessary to say that sometimes GDAL library installation can be problematic. Therefore, it is recommended to install this library from the wheel file. These files, in version for Windows and Linux, can be found in the SAET installation folder. We don't have to forget that we are going to download images from ESA and USGS servers. Therefore, before using SAET, we must register as users in these websites. You have the links in this slide. From Copernicus Open Access Hub service, this is the suitable link. In the case of USGS service, you must register in 2 services, the USGS Eros web service and the machine-to-machine service. From each service, you will obtain your credentials, user and password. Once you have your credentials, you must open the SAET configuration file, saetconfig.py, and replace the asterisk characters with your own credentials. Now we are going to talk about the parameters to run SAET. Some of them are configured from the SAET configuration file, but most of them are used from the command line. First, let's see the basic parameters. The blue color means that the parameter is required. The green color means that the parameter is not required. The red color indicates the default value for a parameter. Taking this into account, the basic parameters are the following. The running mode. SAET has 4 running modes: only searching, downloading and processing, only downloading, and only processing. This last mode is in case you want to reprocess images that have been downloaded previously. Area of interest. We can specify a file in JSON format or using latitude and longitude coordinates. If we set this parameter as none, we are indicating SAET that we will search for images using the name of the scenes. Start date, central date, and end date. This is the range of dates around the central date of the storm, which is supposed to be the peak of the storm. Cloud coverage. This is cloud coverage percentage to filter cloudy images. Landsat products and Sentinel-2 products. Indicate the type of products to be downloaded, Sentinel-2 in 2 levels of processing and Landsat in 2 collection and 2 levels of processing. List of Sentinel-2 and Landsat scene. List of scene to be downloaded. This parameter will be used only if the parameter area of interest is set to none. With respect to the advanced parameters, they allow to customize the default value of some key aspects of the extraction algorithm to adapt the results to the user requirements. For example, sometimes the water index used does not define the land-water interface correctly, so we can use other water index and/or other threshold methods. On the other hand, the cloud max band provided by Sentinel-2 or Landsat-8 or 9 contains some mistakes, misclassification errors for example, so we can decide to use all the classes of the cloud mask, only some of them, or not use them at all. Finally, we can also choose different kernel size of analysis for the extraction algorithm if needed. According to these ideas, the advanced parameters are the following. Output data folder. By default, the results will be stored under SAET folder, but the user can change this path. Water index type, thresholding method, morphological method, and cloud mask severity. They are parameters related to the approximate pixel line determination. And kernel size, which is the parameter related with the approximate subpixel line determination. Before running SAET, we must decide which run mode will be used. If it's the first time that we use SAET in a project, we are going to use the only searching mode. This mode will allow us to search for the most suitable pre-store and post-store images, namely those that meet the date range and the percentage of cloud coverage criteria. Once we know which images we want to process, we can choose between the mode downloading and processing or only downloading. The former one downloads and processes each image consecutively, whereas the latest only downloads the images which will be processed in another moment. For example, if we know that the Copernicus server will be closed for a while due to maintenance tasks, we can decide to download all images in advance in order to prevent downloading problems. Finally, if we have downloaded several images previously, we can process them or reprocess them without having to download them again. Before saying an example of use with SAET, it is worth explaining how to use the pitch polygon file. SAET uses this file to analyze only the pitch polygons along the European coast. Therefore, if we want to run SAET for another coast outside Europe, we can add new polygons to this file. The only requirement is to maintain the field beach code, which contains unique identifiers for these polygons. At this point, it is important to remark that the user can add new polygons or modify those with errors in its geometry. Now, we're going to use SAET in a real test case. Concretely, we're going to study the effect of the Gloria storm on the Valencian coast in January 2020. Gloria storm caused a big impact on the Valencian beaches with a lot of damage to infrastructures and people. The first step before using SAET is to see which is the affected area and which images Sentinel-2 or Landsat-2 or 9 are involved. For this reason, SAET includes in the folder aux data a QGIS project called Map Director that can help us in this task. Open this file. It contains 3 layers, the beach polygon shapefile and the 2 shapefiles with the grid polygons for Sentinel-2 and Landsat. In this case, we are going to use Sentinel-2 images, so select the Sentinel-2 tile that covers the affected area. This tile has the name 30SYJ. This name will be used later when we run SAET. To run SAET, we must go to the SAET installation folder and open a terminal window. Then, as we commented before, the first step is running SAET in only searching mode. In this case, we are going to search for the Sentinel-2 images belonging to the tile 30 SYJ that are inside a range of dates around the peak of the storm, in this case the 20th of March, and that have a percentage of cloud coverage less than 10%. Type the next command and press Enter. SAET offers two types of results: in the window terminal as text and visually as HTML file. In the terminal, SAET presents an ordered by date list showing the position of the central date for the storm with respect to the date of the found images. Along with the identifier of each image, it appears another type of relevant information, like the cloud coverage percentage, the difference in days according to the central date, and the availability of the image. This information is only for Sentinel images. It is important to remark that the number of the image in the list can be used to choose which image or images will be downloaded and processed. In the same way, SAET also displays the thumbnail of every found image with the same information as in text mode. With this information, the user can decide which images will be most suitable to be analyzed. There are some situations where one image must be rejected. For example, if one image has a low percentage of clouds, but these clouds are distributed over the analysis area, this image is not suitable. The same thing happens with those images which have areas with a lack of data. Before continuing, let's see how we can use the Sentinel-2 images that are not available for downloading. This only happens with Sentinel-2 images. In the Copernicus server, the newest images are available, let's say online. After some time, these images are classified as offline and they are deactivated. Before using SAET, it is mandatory to activate again these images. First, we have to visit the Copernicus Open Data Access website in this link. After running SAET in only searching mode, one of the images which we are interested in is offline, completely the image of January 26th. To activate this image, first you must search the image in the server. Type the identifier to the image in the text box and click on the search button. Locate the image in the list and click on the download button. An alert window appears indicating that the image will be available shortly. It's important to remark that the reactivated image will be available only for a few days and only for the user that did the request. Once the image has been reactivated, we can run SAET again, but this time using the mode downloading and processing. To do this, type the same command that we used to search for the images, but changing some parameters. Change the running mode from only searching to downloading and processing. Add the parameter number of products indicating the images to be processed. Remember that this number is the image position in the list of found images. In this case, we select the images 0 and 1, let's say the images of January 60th and January 26th. Then these images are downloaded and processed. In the case of Sentinel-2, the Copernicus server allows us to download single bands, so SAET only will download the necessary bands for the algorithm of shoreline extraction. These pictures show the downloading process and the extraction steps carried out for each image. When the extraction ends, SAET reports the time spent in the process. After finishing, the results are stored in three folders. The folder data that contains the downloaded images and intermediate data created in the process. The folder search data that contains the HTML file that SAET creates in the only searching mode. The folder SDS that contains the extracted shorelines. These shorelines are in both shapefile and JSON format and also as points and lines. Although the source images may have different spatial reference systems, the extracted shorelines are converted to geographic coordinates to facilitate the comparison among shorelines. These pictures show the folder structure previously described. This is the result obtained after running SAET using two Sentinel-2 images. In all, in 10 minutes, 2 tiles were processed, covering a coast length of 123 kilometers with a resolution of 1 point every 5 meters. These pictures show in detail the shorelines pre-storm in green color and post-storm in red color. The results show a clear erosion in the beach areas. We have seen SAET running in the mode downloading and processing. If for any reason we only are interested in downloading images, we will use the mode only downloading. This time, we can use the same command line as in the previous case, but changing the running mode and indicating the number of images to be downloaded. The only processing mode is suitable in 2 cases: processing previously downloaded images for the first time, or reprocessing these images by changing some of the default parameters of the extraction algorithm, like the water index or the cloud max severity, for example. When the user runs this mode, SAET will ask for the number of images to be processed. In this case, the list of available images will be created from the folder data. Here we can see different ways to use this mode: processing images in the data folder by default, processing images stored in another folder, processing images but changing the default values for some parameters. The advantage of this mode is that the user can preprocess an image as many times as needed without having to download it again. Finally, it is important to remark that in each processing the results will be overwritten, so it is recommended to make a copy to preserve previous results. This picture shows the window terminal running SAET in only processing mode. In this new section, we will discuss how to make a brief analysis of the impact of the storm from the extracted shorelines. There are different ways to analyze the impact, but one of them is to link the change between the shorelines before and after the storm to a reference line. This change, expressed in meters, will indicate where and how much erosion or accretion has taken place. In this case, we have a reference line representing the inner line of the pitch. This line is divided into small sectors according to the user needs. In the table of the reference line, the field dl_feed_int contains a unique identifier for each sector. In this case, this identifier corresponds with the length in meters from the first sectors along the reference line. To perform the analysis, we use QGIS, a free open-source geographic information system software. The first step consists of computing the nearest distance between each point of the shoreline and the different sectors in the reference line. We will use the tool distance to nearest hub. After running these tools with both pre-storm and post-storm shorelines, we will obtain 2 tables indicating the identifier and distance to the nearest sector. The fields half_name and half_dist contains this information. Now we have to summarize the information of every sector to compute the average nearest distance from every shoreline to the reference line. By running the tool statistic by categories, we will obtain 2 tables, one for every shoreline. The field half_name contains the identifier of the sector, the field count, the number of associated points, and the field mean, the average distance from the associated points to the sector. Now, we need to join both summarized tables to compute the changes in the average distance for each sector. The first step is to run the tool join attributes by field value, using the field half_name as the join field. Once the 2 tables have been joined, we will create a new field to compute the difference between the average distance in every shoreline for each sector. In this case, we have created the field difference, and the expression to compute the change have been field post mean minus field mean. Finally, in order to represent graphically the changes, we are going to link the previous table to the reference line table. Run again the tool join attributes by field value, using the fields half_name and dl_feed_int as join fields. After that, we will be able to symbolize the reference line according to the field difference. We can notice that all the values are negative, which means a process of erosion. The different colors indicate the sectors where this erosion can cause more problems. To conclude, we will remark some ideas. SAET has been designed for rapid impact analysis linked to the changes produced by strong storms, but it can be used for other many purposes, like recovery analysis, evolution analysis, the study of anthropic actions as constructions or beach nourishments, etc. SAET is very flexible and can be adapted to any type of scenario and requirement. The access of the official imagery source allows being up to date. The open source perspective can contribute to increase the research in the field of evolution and management of the coastal areas. Thank you all, and if you have any questions, do not hesitate to contact me through the email that is displayed in this slide. Thank you very much.